Hello, everyone. Here's my funny slide for what life might be like for Santa Claus in the future with global warming. Anyways, today we're talking about greenhouse heating and some of the strategies. And this is kind of cool. This is these are cold frame boxes, which are just basically repurposed windows over a box in the middle of the winter. And they're growing lettuce underneath those in the middle of the winter. As long as they keep snow off the tops, the lettuce will grow fine. What am I trying to say? That there's plenty of solar energy even in the middle of the winter. Um, this is a nice little greenhouse up on a hill. Look at the snows melting. I bet you it's toasty warm in there right now with no heater on. Now, it's a different story if it's really, really cold, right? So in the previous slide with the cold frames, you would grow crops that are cold tolerant, right? Spinach would be a good one. Why would we use white plastic in the wintertime? So this is often used in a nursery context where they're growing perennials and shrubs, rhododendrons, things like that. And the main reason being that in the winter, we want those plants to stay dormant. So white light actually reflects a lot of the solar radiation back into the sky, and it keeps the temperature cold inside the hoop house. We don't want those plants to wake up. They have to stay dormant. So that's why we use a white film on hoop houses at nurseries. Looking at a greenhouse, if you look at the date down here, this is January 26th of 2013. Coldest time of the year for our area. This is a greenhouse in Niagara. On the side is watts per square meter, and you're peaking at 450 watts, 560 watts, dips in the middle of the day a little bit, but the overall heat integrated, if you calculate 300 watts per square meter, works out to 3,000 kilowatts per hectare, and that works out in terms of heat. We'll talk about this math in the winter, but in the next term, but not a great deal, but that's 10.2 million BTUs per hectare per hour. That's the equivalent to a 300 horsepower boiler of heat coming from the sun in the middle of the day in January. So that's a lot of heat that's for free. And this is where greenhouses that's their real strength, right? Oftentimes people talk about indoor farming and stuff like that, and I think they fail to remember that there are some real benefits to greenhouses thermally. Um, so often in the middle of the winter, this graph here, the yellow line on this side, is heating, and on this side, the blue line is cooling. And in fact, what's happening is, whoops, the greenhouse is actually venting heat out of the greenhouse during those peak times to keep the greenhouse cool. So venting happens even in the dead of winter. Keep that in mind as we talk about snow on top of greenhouses and stuff. So what do we need to heat greenhouses, right? We talk about energy being put in, right? So you have a boiler or a furnace that's adding heat, and how do we compensate for the heat loss, right? So heat is lost through things like convection. So warm air rises out and off the surface, it radiates off the surface. You get evaporative energy absorption from plants. As water is evaporating, it absorbs latent heat, which cools the air. You also get conduction from the greenhouse into the ground. So these are all the ways that greenhouses lose heat. Important to remember those for your final exam. I asked those questions. So convection of warm air to outside, right? So leaking and out through cracks. Radiation, so radiates off the surface of the greenhouse, so the surface is warm, so it gives off heat. Evaporation inside, so plants inside the greenhouse actually cool the environment by absorbing heat from evaporation of water. And then lastly, conduction into the ground. So there's your greenhouse, it's sitting on the ground, it's all nice and warm. It's not really warm, but some of the heat actually goes into the ground. It's lost to the surface of the earth. All right, so conduction. All right, let's clean that up. As far as heat, we have solar radiation gain. which is what we just talked about before. So sun, light power. And then, of course, there's our furnaces, boilers, furnace. So we can use conduction, convection from floor or heating pipes. Wow, I'm just terrible with the circles today. Floor and heating pipes, or maybe a vent if you're blowing hot air. But that's really uncommon in a modern greenhouse, maybe in a cold frame. Um, Again, we'll touch on some of this in the winter, but just summarize. There's some ways that we get heat from electricity, natural gas, oil, coal, wood, or other biomass, or maybe even industrial waste heat. We won't be going for a tour this year, but there's a greenhouse close to London that is right across the road from an ethanol plant that takes corn and makes ethanol to blend with their gasoline. And in the process of fermenting the corn, it generates quite a bit of heat. And that heat is actually piped across the road into the greenhouse on the other side, and they grow tomatoes. And on top of that, when you ferment corn to make alcohol, it produces CO2. And the gas is collected and put into the greenhouse to feed the crop. So it's a real cool modern example of efficiencies with energy. Um, This is a snapshot of a greenhouse that heats with wood. This is actually a cucumber greenhouse up in Flamborough called Beverly. This is a massive warehouse packed full of wood fiber that they burn to heat their cucumbers. This is all reclaimed waste wood. It is not trees that are shredded. It's stuff that would be normally put into a landfill. So it's diverted and then filtered and shredded, and then they combust it with fairly efficient boilers. So it's a low cost, sustainable way to heat their greenhouse. Beverly Greenhouses, I believe, is a 30-acre greenhouse. They grow just cucumbers. Um, they supply all the cucumbers to Costco in Ontario, Quebec, Manitoba, and then I think they sell cucumbers into the States. But any cucumbers you buy at Costco are from this greenhouse. Um, When we talk about heating, there's what we call high pipes and low pipes in a greenhouse. So overhead pipes, bottom heat under benches on the ground, and then there's another one we call activation pipes. So let's summarize let's look at what these are um, and in a context. So here's a picture of overhead pipes in a greenhouse. So there's your energy curtain at the top, and then you've got your pipes running along over top the crop, right? There's your crop. These are the overhead pipes. We're going to get more into their function as we go through. Bottom heat under the bench. Here's heating pipes. Here's bottom heat in the floor, so in-ground bottom heat. Here's an interesting approach where they put heating pipes right in the bench. They loop underneath the entire bench, bringing heat directly to the pots. A lot of people have experimented with this system. With certain crops, it works really, really well, and you save a lot of energy because all you're doing is heating a little zone around the bench. The rest of the greenhouse can stay cold for the most part. Some crops do well like that, others don't. So it really depends on what you're growing. Activation pipes. This is principally vegetable growing greenhouses. So we have bottom heat pipes down underneath the troughs. We have overhead pipes up by the gutters, and then there's pipes in amongst the crop where the fruit is, right around that height. And their job is to activate the crop. In other words, what that means is they warm the vegetation and the fruit in that vicinity, causing localized transpiration to help get the plant woken up and active and keep things moving. This is a tomato house that's been planted this is 2 weeks in, and you can see the context here. We have our under plant heating pipes, which also double as a rail for stuff to roll on. So your sprayers, your staff, when they work in the crops, they're on electric carts that roll back and forth on these heating pipes, so they don't have to walk everywhere. And then there's the overhead pipes up by the gutter. You can see these things generating heat at the top of the greenhouse. And then there's your activation in the middle of the crop. Now the crop's very small, hasn't grown past them yet, but that will be in the activation zone. And these you can raise and lower. These cables will bring them up or down depending on what you're growing, the height of the crop, that kind of thing. Okay, so let's summarize these. Overhead heating pipes, right? So higher energy loss, right? Because you're putting heat at the top of the greenhouse, which seems inefficient, but you have the ability to run them at higher temperature, which produces infrared heat, which then will radiate down and give you a higher leaf temperature. Bottom heat, which is more efficient because it's heating the plant space, like right where the plants are, is helpful, but oftentimes because it's underneath the top, the roots are warmer than the top. And is that a problem? Well, it's hard to say. When you're trying to root something, so having warm soil will encourage roots to form on cuttings. But generally speaking, once a plant is established, if the root zone is warmer than the leaves, we have a higher respiration in the roots. And sugars flow to the roots and less so to the flowers or fruit. So that's not altogether desirable once you get a mature crop. Activation pipes, these are for uniform leaf temperature in tall crops like those high wire tomatoes, cucumbers, peppers. And they supply energy directly to the foliage, right? That's going back to the sort of balance between root and foliage temperature. Activation pipes also encourage transpiration because you're just driving air up as it heats and then out to the top, helping to move air through the crop gently. Overhead heating pipes are often used for melting snow, getting it off the glass so you can get light into the greenhouse or prevent damage. For example, with ice and opening vents. Typically, if you're running your overhead pipes hot enough, right? So if the temperature is high, it actually will start to radiate heat. And that radiant heat will then radiate back down regardless of airflow and dry or heat the leaves and encourage transpiration. So on the right context, they can be very useful. Or for example, drying leaves before the evening if you have a crop that's really prone to powdery mildew. What do we mean by radiation, right? So we're not talking about this kind of radiation. We're talking about radiant heat. If you are ever by a fire, you put your hands over the fire, that's convective heat. That's going to burn your hands, right? Whereas sideways heat, it's not flowing with the air, it's light. It's actually light coming out the fire that radiates to your hands, warming them directly. So that's how you can sort of visualize the difference between convective and radiant heat. And then conductant heat, right? So this is a metal poker. It absorbs heat and conducts it along. So that's sort of like our greenhouse structure conducts heat to the outside. That's one of our ways of losing heat. As far as heating pipe, if this is a heating pipe in the center, these circles here, right? That's a heating pipe. The heating pipe changes its properties depending on the temperature. So when the temperature is really high and we have radiant heat, it's shooting light heat out in all directions, radiating in all directions. If the temperature is low, it tends to just cause convective heat, which warms the air in close contact, which then rises, meaning you get convection heat off the pipe, but it's not radiating heat. I hope that makes sense. We're going to touch on it again a few slides here to make sure you follow along. So why not just run pipes at high temperature all the time, right? Well, first of all, it's expensive. And then if you're running really high temperatures in order to get radiant, you're also going to get really high convective, which means your greenhouse is going to overheat. Then you're going to have to vent, and now you're losing lots of money. So radiant heat is used sporadically and when it's needed. For example, going into the evening, trying to dry your crop to make sure there's no powdery mildew risks for the night. Looking at activation pipes, they're typically located directly within the canopy, right? They encourage air movement upwards through the crop, warming them, activating them. Of course, that also means if you're warming your leaves, you can have lower outside temperature. So you can actually have a lower temperature beyond the plants as long as you have heat within the plants. And then, of course, from a disease prevention perspective, you're removing moisture and encouraging transpiration. And then lastly, and this is especially important for tomatoes, by warming the fruit, we actually steer sugars, the flap, so the phloem will flow sugars to the fruit, which are warmer. That's how we can improve the flavor of the tomatoes, is by using activation pipe temperatures. Notice we're going to talk about this next week, but this tube, this clear tube here, is actually a CO2 gas tube. So not only do you deliver heat in the middle of the crop, you're also delivering CO2 directly to the canopy. So as that air moves up to the crop, it picks up the CO2 and delivers it to the leaves, enhancing the growth and productivity, yield, etc. Bottom heat. This picture, they're really fine arrows, but it's actually an engineering model, a modeling image of how air would flow in the greenhouse with bottom heat. And you see all the arrows are kind of flowing like a current, swirling up the sides, are coming like this, around, down, and cooling on the outside wall and coming down. I, I want you to try to visualize how the air flows, because that's really helpful when you're understanding how your greenhouse works, wherever you end up working, to try to manipulate the heating pipes to get your climate the way you'd like it. But there's definitely airflow. So with bottom heat pipes, we're only heating the air. We're not heating the plants because there's no radiant heat, because they're normally not really, really hot. And that air then moves by and has to be warmer, and it transfers heat to the leaves, to the plant. Now, if you do have radiant and convective heat, it depends on the context. So, for example, this picture on the left is in-floor concrete heating, which means that they put all these heating pipes down, then they cover the entire greenhouse with concrete. So the floor is heated. In this context, we have heating pipes. So what I'm trying to say here is that with concrete, we cannot run really, really high radiant temperatures because it cracks the concrete. It's kind of funny that they actually call it radiant heat, because it's really not. It's actually a gentle heat that warms air right on the surface of the concrete, which then moves up, giving you some warmth. Whereas these heating pipes, because they're not in the ground, they're not going to break concrete through expansion and contraction. They can be low temperature, causing mild convection up to the bench, or they can be really hot, causing radiant heat. But generally speaking, underneath the bench, you're not likely to run your pipes that hot, unless it's a real cold, cold winter day. But as the heat goes up, your proportion of radiation increases relative to convection. So this is a diagram I tried to make to help describe what I'm talking about. In a convection condition, this is where heating pipes are sort of normal temperatures. You have air being warmed and rising up to the benches, and then under the gutter you have air being warmed, rising up to the glass, cooling, and then falling down. And on the edges, we have pipes on the perimeters of the greenhouse that warm the air, causing it to go up, hits the glass and cools and comes down. So there's all sorts of flow and movement of air throughout the greenhouse. With radiant, we are generally just radiantly heating the crop directly. And then the air is cool, which of course, what radiant convection comes off the bottom, there's no more pipes up here, there's no perimeter pipes. In this context, the heated air quickly cools and falls back down on the bench. And you sort of like have a boiling surface of air that is warm. And it's not exactly stirring the entire climate. So you don't get drying on the glass, you might have condensation. It's not an ideal situation. So the question here, HAF, this is horizontal air fan. So in this context, having fans that are stirring the air would help to move that around and get a better, more uniform climate. This is something called a convectube. It's actually a trademark. It's a poly tube, and you'll see there's holes punched in the sides. and this cinches onto a fan which blows the air into it from the greenhouse. And in some greenhouses that are maybe poorly designed for heat distribution, they will suck warm air in from the climate, blow it down the tube, and then the tube dispenses the air out the sides down the entire length of the greenhouse, and you get a more uniform temperature. So these tubes deliver the warm air. It is helpful in greenhouses that are old and you're trying to retrofit to make them work better. In a modern greenhouse that's properly designed, these are not necessary. But there are some greenhouses around that use them. It is important that you change this polytube every few years because they get dusty and dirty and they block a lot of light. Some farmers don't like to change them and they look pretty ugly. So these are just a series of pictures showing you different heating configurations and how the air flows. Just to give you a better sense of how to visualize what happens in terms of, just perimeter heat, circulating a rather coarse circle, one single convectube without air fans and perimeter heat, not getting a lot of air in this area. Multiple hot air tubes, getting some movement, not bad. Exchange. The idea being, of course, the most uniform heat we can get, the better. Just to give you some examples of how different examples might look. So again, radiant heat heats plant tissue directly. So in that case, in radiant heat, the plant temperature is often greater than the air temperature. And with convection heat, the plant temperature at your best is equal to air or less than air temperature. So a couple of key sort of logic things to remember. In terms of hot air, air is always warmer than the plant. There's no radiant component to heat transfer. With hot water, this is like a hot air furnace or blowing hot air through a convectube. With hot water heat in pipes, you can have a radiant component if you run the pipes hot enough. And that, of course, the radiation component increases and the plant temperature increases more than the air. So that could be a real savings from an energy perspective. Just have to make sure you don't overdo it. Okay, for the rest of this stuff, I've got a few scenarios just to sort of talk through some of the logic here, right? So scenario one, we have a rooting bench. Where do we want the heat? Right? So what's the question? Where do you want the heat on a rooting bench? We've talked about this before. We want bottom heat underneath the cuttings to encourage sugars to flow to the bottom of the cutting to get roots to grow, right? So how do we achieve that? There's two ways. You're not going to blow warm air under, so you're going to either have underwater heat pipes, which is what we have here, heating pipes, or you can have smaller heating pipes directly on the bench. That might even be more ideal. In the old horticultural days, they would run electric heating wires in sand and then lay the flats on top of the sand. And that sand was sort of a thermal mass that would warm the bottom of the tray. What are the risks? Well, not a lot. I mean, we have to do this. I suppose there's the possibility that the top part of the tray is too cold and you might get rot if it's the extreme warm below and really cold on top, but that's unlikely. I haven't seen that happen many times, so there's not a lot of risks. Scenario two, cut flowers grown in the ground. Where do you want the heat? Well, look at this picture. I don't see any heating pipes up here. There's a few. These are heating pipes. There's a few above. That's helpful, but realistically, we want to get the heat down into the crop, right? So that the air is moving up through the foliage, creating an active environment. This is a picture of a cut Lysianthus farm, and you'll see that the heating pipes are down right near the surface of the soil. So as the crop grows up over the heating pipes, now the air flows up through the crop, creating an active environment. With high wire vegetables, where do you want heat? Well, we talked about this. We want it under the gutter, we want it within the crop, and below the crop. So there's 3 layers. Remember the activation pipes, that's an important one. And then down below here are our bottom pipes, which also serve as a mode of transportation. Here you can see there's a cart rolling on there. The person's just pushing it in that context. There's your activation pipes. Lots of fruit here. This is a high greenhouse. Unlike ours, they can afford to have the vines high with lots of leaves removed so that the fruit gets lots of light. Good airflow. Remember, leaves down here don't get as much light, so they don't produce much sugar. They just get in the way. So they often just rip them off as they lower the vines and throw the leaves on the ground here. They get cleaned up periodically. Scenario, plants on the ground. Let's say this is a fall mum, mass-produced fall mum crop in a greenhouse. There's overhead pipes, right? So what can we do with those? Well, it's hard to get air to convect from there down to the bottom. You'll get some movement, but not a lot. So one thing we can do is we can run these pipes at high temperature, causing radiant heat, which will radiate down and warm the plants directly, right? So radiate to the plants. But often the case often would be that there's pipes in the ground, if possible, underneath this. Now, I bet anything this greenhouse is just straight ground cover. It's probably more of a bedding plant business, so they don't need as much heat. They probably just have the overhead pipes, which would be the bare minimum. But you can, like we said earlier, you can put pipes in the floor and then cover those with concrete or cloth, and then you have gentle heat underneath the entire crop. This is often the case with flood floors like concrete. When they pour the concrete for the flood floor, there's heating pipes inside here, and that creates warmth that moves up through the plants. Just convective warmth, not radiant. That would cook the roots. So this greenhouse would have, you've got your pipes running lengthwise, and you've got flood floors under here with heat. You've got nice uniform heat in all locations. And you might even notice that there's perimeter heat, these pipes on the sides. And that's to make sure that you don't get cold edges, because you're filling your greenhouse right to the side wall. And in the winter, cold air pours down this wall and can impact your crop. And your edges, the plants may actually be immature and not fully grown. So by having heating pipes on the side wall, we actually stir the air and keep the air moving away and up. And so your crop on the edge grows at the same rate as everything else. That's a really important point. You'll see those at the college. To some of you, I'd mentioned the Earthgood floor. This is a link. If you click on that in your PowerPoint, they'll take you to the company's website where they talk about it. This is a flood floor with a porous mat, and they often have heating pipes underneath in here which generate heat from below, as well as provide a place for water to come up to flood the plants and then drain back down and away. And you have a airflow underneath, so it's not like the plant is sitting on a wet, cold concrete floor or something like that. Pretty good system. It's becoming very popular. Rolling bench scenario. Where do we want the heat? Well, we want it underneath, right? Pipes underneath. Is that the only place we want it? No, we want radiant heat above. And we can see in this picture, there's actually radiant pipes in the background, and there's some between the posts. So not only do we have heat below, but we have heat above, and that allows us to get the air moving in all directions. Plus, it gives us the benefit of radiant heat if we need to dry the crop. A lot of drawing there, sorry. Another scenario, snow in the greenhouse. So let's say you've got snow and it lands and it doesn't melt because your energy curtain's closed. Now you've got entire greenhouse covered in snow. But look at this. Look at the weather. This is sunny, and this greenhouse has snow all over it. They're going to lose a potentially really nice day's worth of sun and growth because they haven't melted the snow off their greenhouse. So in the one hand, they may feel like they save money, but their crop would really have benefited from getting that sunlight for that day. So we really have to be on top of melting our snow when it arrives, for two reasons. Not only does it allow us to take advantage of sunny weather, but if this snow started to melt and it was a really hot day, the light that gets through would actually start spiking the temperature in the greenhouse, and it could get really hot. And because there's snow in the vents, you can't open them. So now you're in trouble, right? Your temperature is climbing, and you have no way to cool the greenhouse. March is the most troublesome time of the year for this scenario. So it's important that you keep on top of that. Just like this graph shows, in the middle of January, there's actually vents are opening to let heat out. So you need to be aware that your vents have to be free and clear so that you can operate them. So if it snows one day, make sure you melt the snow. And then at least first thing in the morning, open the energy curtains early. Turn your top heating pipes on to get that heat at the surface, the top of the greenhouse, to melt that snow as quickly as possible. Always know the forecast. All right, I think this is the last slide. So my goal here today was to make sure you understand the difference between convective and radiant heat with hot water systems, understand the role of bottom heat, activation pipes, and top heat, perimeter heating, melting snow with under the gutter heat pipes, and then just generally visualizing how air will flow in a greenhouse with the different types of heating pipes. All right. Hope you got something out of that.